welcome back. I'm going to start the second lecture. So I'm still Francis Bach, this has not changed. So are still my kids, still very nice. Yeah, so we see like the master problem which we're solving here. So we have observation xi, yi, id. We do like linear predictions. This has not changed. We have this convex data fitting term that we aim to look at. We had like three losses which we really liked. One was non-smooth, okay, the hinge loss. One was logistic, and we had least squares. So least squares has not come as being special for the moment, but it will come up more today. And there was like two quantities, okay, f was the expected risk, and f hat was the trailing risk. So we had access to f hat, but you really care about f. Then we saw like method for optimization, and the standard one was gradient descent. And to apply gradient descent, you need to know g. Okay, you need to know the function g. So this has to be the empirical risk. And all my bounds was with g star being the optimizer of the empirical risk. Okay, so this is important. So when you do optimization, you have a function g. Don't care whether it comes from learning, processing, whatever. You want to optimize it. And theta star was the optimal value. What we're going to do now, theta star will be the minimum of the expected risk. It will be the best possible predictor in the class for unseen data. So this will be important. And what we saw at the end is that one. Okay, so from the statistical side, we know that when you replace the true risk by the empirical risk, you have this error of 1 over root n. And if you combine it with the error of subgradient descent, which is as 1 over root t, you take t equals n and then match, and you get this complexity of n squared. Okay, so this was where we ended up before lunch. Now we're going to do improve that O over n squared to O over n. So now let's look how this works. So what will be our goal now will be to minimize the function which we don't observe. Okay, so if you remember anything from the class, is that when you use stochastic approximation, you are minimizing something which you don't observe. What you only observe is not the gradient, but a noisy version of the gradients. And I will call f prime n of theta n the gradient which is noisy, which I observe at time n. The key is you need something. Okay, it has to be noisy, and you assume it has the correct expectation. Okay, so you have the true gradient, and you oscillate around the true gradient. Another key aspect is that you don't need the variance of that gradient to go to 0. You can always make errors, as long as those errors are random and they have the correct expectation, that's 0 here, then you always converge. Okay, so if you remove the unbiasedness, so if you have like deterministic errors, you will not converge if the errors are nasty. Okay, so whatever your algorithm can construct a sequence of errors that will drive you to a place where you don't want. If the errors are random, this will never happen, even though their magnitude may not go to 0. So this is the setup. So in the context of machine learning, there's a very simple way of defining a noisy gradient is to simply look at a single observation. Okay, so this is very, very classical. So like this morning, I will call fn of theta the loss associated with a single pair of observations, xn, yn. I'm still doing linear predictions. And the key is that if you take the expected value of fn, since I have assumed that my data are ID, they all come from the same distribution. For all n, the expectation is the risk, the true risk, the generalization error. And this is simply using the fact that we are ID. Then, if you compute the gradient of the expected risk, if you're willing to invert differentiation and expectation, then the expected value of the gradient of a single observation, which is written over there. So this is L prime is the derivative with respect to the second variable. This is a real number times your features. Since I'm doing linear predictions, all of my gradients are proportional to the features. So we are exactly that setup. If I take the gradient of a single observation, its expectation is the gradient of the generalization error. Okay, so this is the key aspect is that we're going to consider now only bound on the testing risk. Okay, so this is to be contrasted with a bound on the empirical risk. One key aspect as well is that the number of iterations will be equal to the number of observations. So there are several reasons to that. The first one is efficiency. Okay, if I only see data point once, of course, this is a single pass algorithm by design, but also because we need those like gradients to be independent. Okay, so as soon as I will see a data point like a function fn twice, then I'm starting to minimize the empirical risk, and this is not what I want to do. In practice, we end up often doing several passes, and this, I will come back to that at the end of it. But clearly, the number of iterations is the number of observations, hence the change in notations. I'm going from n to t, from t to n, okay, just to make sure that n is equal to t. Okay, so here I'm doing a stochastic approximation from a very narrow viewpoint. Okay, I'm considering minimizing a convex function which is defined as something like this. This goes much broader. Okay, this was in fact one of the big chunk which I removed from my master's class, and that chunk is dedicated to algorithms which are of that form. So you take iteration where you go from n-1 to n by subtracting a function for which the expectation given the path is correct. Okay, so h is a gradient mapping in our case, but whenever you have an algorithm like that, when you do a random step, okay, and the expectation of the random step is known, then this is going to convert to a zero of h. So this goes beyond complex problem, beyond ID. There's like 50 years of literature on it, and if you want to know more, there's two reasonable books about it. So here we're going to focus on a narrow problem. We will be able to characterize entirely its behavior. Okay, so the key is we take a smaller problem and try to understand it totally. So there are like three frameworks to learning with data, which I want to discuss to make sure that things are clear. What I'm going to consider now is stochastic approximation. So I have a function f, which is the expectation of a certain loss given some data. Okay, z is x, y in my case. Okay, so now I'm going to do that gradient descent type technique by assuming I can sample from z. Okay, so you see what I'm going to do. I sample from z, make a step. What I have discussed like before lunch was a so-called batch learning. I assume I have a finite set of observations, z1 to zn. I build the empirical risk, and I'm using like generic complex optimization to minimize this empirical risk. I need to put some constraints, otherwise I may overfit. And typically, to make sure that you go from f hat to f, you need some concentration result. You need to show that, to ensure that f hat is close to f. If f hat was very far from f, minimizing f hat would not do anything for f. Okay, this is a batch. There is something else, which is called online learning, which I won't cover, which I will not cover in this talk, where data arrives sequentially, and you need to make a prediction at every step. Okay, so you receive a data point, you make a prediction, receive a loss, and go on. So at the end, you judge not on the quality of the predictor at the end of the optimization, but as a cumulative loss throughout the run of the algorithm. You receive zk, you apply the current predictor to zk, you get a loss, and you take the average of this. So this is used a lot in computer science. This is more like the statistical side. Essentially, they are very close. Okay, whenever you have an algorithm for one, you almost have an algorithm for the other. And I let you look at this nice paper by Savianki and by also a nice monograph by Bach as well, showing the differences. Okay, so online learning is by definition this, and the key is that the Z may not be random. Okay, so the Z may be adversarial. Okay, so an opponent may choose the Z in a very adversarial way, whereas in the stochastic setup, the Z are ID from a given distribution. The Z are not allowed to do something different because the Z do not see your predictors. Okay, so this is a bit simpler. So this is a subcase of that when you assume the Z are IDs. But online learning covers a much broader setup. And this being said, I will not really talk about it so much. But keep in mind that whenever you see online learning, you're not very far. Okay, so I'm going to consider like the stochastic approximation setup. And like for the deterministic optimization, we need some assumptions. Okay, still like boundedness of gradient, boundedness of Hessians is equivalent, or strong convexity. So the key algorithm is stochastic gradient descent, which is the worst possible name for an algorithm. Why is it a very bad name? SGD? No. It's cool. Okay, it's nice abbreviation. There are two reasons for a bad name. No. But the first one on the slide. This is a Robinson-Monroe algorithm, in fact, okay, applied to a specific problem. It's not a big issue. The issue is descent. It is not a descent algorithm. Okay, so when you make a random step, you may go up in the full function. Okay, in fact, in any good run of SGD, you're going to oscillate a bit, and you go down on average, but you don't always go down. Okay, it's still called SGD for I don't know why. And what is SGD? This you go from step n-1 to n. So here I've switched from index t to index n to highlight the fact that I will see one observation for every n. And I make a step size, I make a step in the negative direction of the stochastic gradient. So we need like averaging. Okay, so it's often called like Polyak-Rupert averaging in that setup. The key is that there is no interaction between this iteration and the averaging. This is offline averaging. Okay? We don't put f prime n of theta bar n minus 1. Okay? We simply do averaging, and on the side, of course, you can update this average online. Okay? You want to compute this at every iteration. But the key issue is what should the step size be? Okay? So what we saw for deterministic gradient descent is that if you're smooth, you can use constant. And if you're non-smooth, you have to use the decaying step size. Okay? So those setups for the step size is not totally correct. And so for stochastic optimization, and we need to use the decaying step size. And the question is, how should it decay? So if you took the same class 50 years ago, then people would have said the best step size is 1 over n. Okay, and some people still say this still today. This is not good. Why is this not good? It is not good because this is well adapted to a strongly convex problem. If you have a well-conditioned problem, okay, then it's going to work. The problem is that many model problems are not well-conditioned, so that step size as 1 over n will not converge, and people now propose more 1 over root n, which I will discuss more now. And what I will show later on this afternoon is even a constant step size. Okay, so step size are going bigger as the problem gets harder. So it's a bit counterintuitive. Okay? So in a sense, you would say, if the problem gets too hard, I should have small steps because I want to be more conservative. This is the opposite. You do a bigger steps, and the key will be averaging will be the key of the key. Okay, so in terms of behavior, okay, you want this to be applicable to supervised learning. One problem is robustness and adaptivity. Okay, so this may look like a very minor issue, but in practice, this is the difference between something that works and something that doesn't work. What is robustness? Robustness is, do I need to the constants? Do I need to know the constants in advance? Okay, so for example, L and U and B, those are those constants. I can estimate them, but often I get very loose bounds. Okay, and if being robust means that even if I give the bad value, I get a good behavior. Okay, so this is true for gradient descent. For example, for gradient descent, if you give a constant step size, you do not need to give the strong convexity constant. The mu is not needed. You just take 1 over L, it's going to adapt to the best possible value of mu. So gradient descent in the deterministic setup is robust. And adaptive. Adaptive means that if you're locally strongly convex, okay, then locally it's going to be faster. So this is really what we want. This is not totally true for stochastic gradient descent. We still don't get its full adaptivity. Okay, so one other thing is that this is one line of code. Okay, so maybe I have this on the later slide. Let's say it now. At the end, the learning is done in one line. Okay, this does not mean that to do machine learning you need one line of code. You need like thousands or millions to access the function and the features. Okay, so once you have the features loaded, the learning is really simple. I'm going to study this single line of code today. So let's start the simplest setup. Let's assume just like the weakest possible assumption, which is like a non-smooth loss, and we're going to replace now like projected subgradient by projected like stochastic subgradient. So now I have some functions fn. This will be the loss for my observation number n. We assume they're all ID. They have the correct expectation f, which is like my performance on unseen data. And now theta star is the global optimum of this test error. This is my best possible predictor in my class. Okay, so this is something which I don't have access to. Okay, so this is, given that I have made some assumptions regarding my predictions, linear and math features, this is the best I can do on infinite data. So this is the algorithm. And the analysis, and if you look carefully, is exactly, the bound is exactly the same as before. Okay, so what has changed from before? Before, we had t instead of n, okay, fine, and we had no expectations. So here, what do we have an expectation? Because I'm assuming my data are random. Okay, this is expectations. This is an expectation of the randomness of my data. F is not a random quantity. This is itself an expectation, but this is not random. And this is the test error minus the optimal test error goes down to 0 as 1 over root n. Okay, so as I get more and more observations, I do conserve my optimal test error. This is the best we can do. Okay, so I will not give any details for that, but this 1 over root n is the best we can do. And the running time complexity by design is dn. Why dn? Because at every time step, I have to access a gradient, which is O of d, and I have to subtract it, which is O of d. So since I make n steps, I get O of nd. And with that, you see that you recover this 1 over root n from before with only O of nd iterations. So this is essentially what the goal was, is to show that by using stochastic gradient, you get this 1 over root n with complexity O of nd. Let's look at the same plan proof. Okay, so what I will do, I will go over the proof, and you will see nothing is changing. Nothing, almost nothing, only the red is changing. So this is my iteration, like stochastic subgradient. This is my step size. And we need to introduce something which is the information up to time n. Okay, so I will call that like a capital Fn. Okay, and this is like the concatenation of my observations up to time n. Then I make some assumptions, and I can use the exact same proof. I'm going to consider the distance to optimum. I can use contractivity of projections. Okay, this we have done. We have seen this before the break, and so you get that this is less than this quantity. Then you can explain this quantity. This is like a square norm. This is the first square term. This is the second square term where you use the fact that the gradients are bounded, and this is the cross product. Okay, this is exactly the same as before. Now, what I'm going to do, I'm going to take expectations. Okay, given the past. What is key of doing things given the past is that, given the past, theta m minus 1 is constant. Okay, this belongs to the past, so this is a constant value. The only random quantity given the past is fn. Okay, theta m minus 1 is the past, gamma n will be deterministic. So whenever I take an expectation number there, everything which is dependent on the past will remain intact, and the only thing which is not dependent is fn prime. So fn prime becomes f prime. Okay, so you transform this stochastic gradient into the full gradient, and now you move on to the proof. You use the fact that this quantity is a surrogate to the distance to optimum, and now you take a full expectation. Okay, so by the towering law of expectations, this get that, and then you put expectations, and what you recover is the exact same equation as before lunch, where I've added a few expectations. Okay, so f is non-random. This is random because theta n minus 1 is random, and those two are random. So this means that the exact same algebra will lead to the exact same result, and that exact same result is this one. Okay, so this is, I guess this is over there. So I have not put the details, but at the end, you recover the exact same result by just realizing that the way you analyze the algorithm is independent of having a random gradient or not. Okay, so this is the key result, showing that combining, optimizing with only a single pass is advantageous. Any questions on that? Well, it's really a three-line proof. and half, let's say like more than half of the papers on optimization, they reduce it to time proof. Okay? Not all, but most of them. Mm-hmm.
This is the result regarding the expectation. Do you have concentration on the variance?
When?
This is the result and the expectation.
Yep.
Do you have a result and the variance?
Okay, so the question is, okay, this is a result and expectation. Do I know a bit more about the deviations? I do, and this will be in the next slide. Next slides. Okay. So clearly, if the expectations was correct, but it was highly variable, this will not be a good thing. This is not the case. Okay, then I can go strongly convex. Okay, so there's nothing new compared to the rest. If I assume that my functions are strongly convex, I have curvature everywhere, then I do a different step size, 1 over nu, and I get a different averaging, and I get 1 over nu. Okay, so this is also something which is not different than from the non-stochastic setup. The key is that you replace the true gradient by the stochastic gradient to get the exact same bound by replacing t by m. And again, this is the best you can do according to those guys. Oh, by the way, this is hard to read. This is really the easier to read. The proof is the same, blah, 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 and something like that. Okay, this is your result for you. Okay, so it's a typical result. You have a result in expectation, okay, which is like 3 lines of proof. And you may want to consider like high probability bound. Okay, so that the probability that you deviate, the probability that your error on top of the optimal prediction is greater than epsilon, you want this to be small. The first possibility is to use Markov inequality, which is what I have used there. The probability that this is more than epsilon is less than the expectation over epsilon. This is what I have. This is a rather weak bound. Okay, so typically when you want to do like bound high probability, you like this epsilon to become an exponential of minus epsilon. Yeah, so you want the probability to decay exponentially as you get further away. Okay, this is what people call like concentration, and you can show you can show concentration essentially this way. This is in a nice paper by Mirovsky and the one by Nesterov. It says the probability that deviates from my bound plus some deviation goes down to 0 exponentially fast. Okay, so we show that this class of algorithm is converging in expectation and in any measure which you might want to look at. So for really the probabilists, I'd like to see convergence in surely there is also a possibility, but this will go beyond the scope of this lecture. Okay. Then, like in the deterministic setup, you may add some things on top of stochastic gradient. If you have like a proximal term, if you have like an L1 norm, and you want to penalize the L1 norm, then essentially you replace the stochastic gradient term by a proximal term, and this works very well. Something which is quite nice when you did it is mirror descent. Okay, so if you want to optimize over like a simplex or over something which is like an L1 norm, there are setups which are a bit better. And there is a nice paper by Mirovsky and Mann showing that you may adapt to the geometry of the underlying set. But all of those techniques, like dual averaging mirror descent, they are very similar to gradient descent. They tend to operate similarly. Some of them are adapted to some setup. So this is just to give references if you want to know. Okay, what I mean by minimax rates. Okay, so this is really one slide to show that what the people I quote are doing. Okay, so typically they want to say, oh, you cannot do better than stochastic gradient. So they have first to assume a model of computation. Okay, cannot do better. It is fine. You have to be given some rules. Okay, the rules of what we call a model of computation, and the rule that we need to consider here is I'm allowed to query a function and a gradient plus some numbers. Okay, this corresponds to the stochastic gradient. You need to define a class of functions. Okay, we consider non-smooth functions on a convex set. And what am I going to consider as a measure of an algorithm for a function f is a value at step n minus the best possible value. Okay, this is what I have considered as a performance measure. For a given algorithm, you want to take the supremum over all functions. I want my algorithm to work as well as I want on my whole class of functions. Okay, take a supremum over the class of function. And what is the minimax performance? This is the infimum over all possible algorithms. Okay, so I want to find the algorithm so that for the worst possible functions, I get the smallest amount. Okay, so this is what people typically try to compute when you study this. If you give an algorithm, you get a bound that this is less than 1 over root n. Okay, so what I've shown is stochastic descent is one algorithm for which you know a bound on this quantity. So give me an algorithm, I get an upper bound. What those guys are showing is providing lower bounds. I will just give you one example of such a lower bound, and this is one by Agarwal et al., which is nice and compact. They show that for the best possible algorithm, you can never beat square root of d over n. So the square root over n of 1 over n is optimal. Okay? So this is one type of result that people are showing, and this is not super easy. Okay? So if you're interested in this, there's a whole business of lower bounds, which is hard to get into, but if you're interested in it, this is one good entry point. So they say that if you beat 1 over root n, there is a problem. And later on today, I will beat 1 over root n. So there will be a problem. And this means that those assumptions will be violated. Okay. All right. So let's look at the summary so far. So we have, this is the same table as this morning. This is like convex, strongly convex, from easy to hard, from hard to easy. So deterministic with 1 over root t, so this is what we had. And we have seen that essentially, when you go stochastic, if you get access to stochastic gradients, essentially you just replace t by n, and there is no loss, at least in the bounds. So your methods are n times faster because you access a single gradient instead of accessing the full gradient. Okay, so this is the cleanest line. Okay, this one is very clean. Not going to go over there. This is a bit less clean, and let's see what we're going to do now. Any questions on what we have seen so far? Okay, so now we have covered essentially this part. Okay, so non-smooth stochastic approximation. Now we're going to go over the two remaining parts, which is like what happens when you go smooth and finite data sets. So the problem when you go smooth, okay, so you have opportunities, and the one which I have mentioned earlier on is the rate at which you forget initial conditions. Okay, so those bounds, all of those bounds, you never see like distance to initial conditions. Okay, to be clear. Okay, so that let's take that one. Okay, so this is a bound, and you see that you have optima of a compact set, and wherever I start from that compact set, the bound is the same. So this has to be a loose bound, because if I start from the solution, I should be faster. When going smooth will allow us to do this, but this will come at a price, and the analysis will be a bit more complicated. Okay, so just a summary of what we have seen, and we have seen that. Okay, so if you work on like non-smooth optimization, the best you could do if you're strongly convex is 1 over nu, and this was achieved by average FGD with a step size decaying with n. Whereas if you just assume convexity, so a harder problem potentially, then you get only 1 over root n, which is achieved by a different step size. You can see from the start that we lose adaptivity to the problem difficulty. You have to know in advance if you're going to be here and there, and adapt the step size. This is the first problem. Then all our rates were global. What do you mean by global? They are true from the start of the algorithm. Okay, they are true for all n, which is to be contrasted with asymptotic rates, which are only true if n is large enough. And if you're willing to go as up, and before I do this, there's a lot of contributions, okay, beyond the setup. Okay, so let's do that. But if you're willing to go asymptotic, Okay, this is nice work by Polakowski and Rupert. They show that if you take a step size which is a bit in between those two, okay, then you could achieve robustness to conditioning. Okay, so you can say I get 1 over n, okay, I get 1 over n, but no presence of mu. Okay, remember that mu in many problems is very small. It can be like 10 to the minus 12. So this is a strong improvement over there and over there. Over there is trivial because you replace 1 over rho 10 by 1 over n, and over there you remove the presence of condition. So this was coming at a price. There were 2 prices. The first price was unit smoothness, okay, where this was true for all possible functions, and the second price was you needed some asymptotic analysis. This is going to be true only when n is very large. Okay, so this means that for n being smaller, this may be a problem. So my goal for the rest of the lecture is to try to go into that and to make this as close to that. Okay, so let's recall what we're going to do. So we have like a stochastic gradient descent. This has not changed. Fn prime is the loss associated with a single pair of observations. I'm going to consider theta bar of n, which is the average iterate, and I'm going to make some assumptions. I'm going to assume that all the fn's are smooth. Okay, so this is what I call a weak assumption because I'm assuming that actually my data are bounded is sufficient if I have a smooth loss, and I'm going to assume that my expectation is strongly convex. Okay, so this typically is a strong assumption, which is only true in low dimensions. You may add a regularizer, but of course that mu now has to depend on n as well, which I don't want to. Okay, so this is I'm going to put results which I obtained with my colleague Eric Moulin, and essentially what we did is to go from the usual setup. So if you open a book by Robin Monroe or a book from the 70s or 80s, you will see that this is the best possible rate, and this is with a step size as 1 over n. So if you open a book even for machine learning in the late 90s, you will see such a step size. Okay, and so what we have shown is that in fact if you do averaging and take a step size which is bigger, then you recover this 1 over n rate. There will be a mu over there, and the key is how you should forget initial conditions. Okay, there are 2 key things: how you forget initial conditions and the robustness of the choice of C. So here I will not talk too much about that, but more focus on the way you forget initial conditions. And what we found is you typically have 2 terms. Terms that I will call somewhat a variance term, okay? The term due to the fact that I have noisy gradients, and a term which is due to the place I'm starting from. If I start very close to the optimum, I should be easier on me. So what we obtain is something of that form. So the details are a bit, I really don't want to go into that so close to lunch, but overall you get the rate at which you forget initial conditions, and the key is that before averaging, you forget them exponentially fast. Okay, so this is nice, is that wherever you start from, you're going to forget. Okay, you converge quickly to a good place, but you pay a price. You pay a price of that price that will. The bigger the step size, the bigger the noise will impact you. Okay, so this is before averaging, and after averaging, so the leading term are in red and blue. Then you lose this 1 over n, okay, you get this optimal rate, but you pay a price in terms of forgetting the initial conditions. So remember that when you do averaging, so if a sequence is converging to a place, if you take the average sequence, it also converges to the same place. It's called the Cesaro theorem. But the problem is that if your original sequence was converging exponentially fast, your average will converge slowly. Okay, so averaging preserves convergence, but will totally kill exponential convergence. And this is actually what we show here, that you lose conditions exponentially fast. The other key thing, this we covered several times today, is the fact that if you do averaging, the final rate does not depend on the step size. Okay, so here the alpha that I've chosen does not appear. Okay, this means that whatever the step size, I end up with the exact same performance. And to highlight this, I'm going to consider very big data, d equals 1. Okay, so I think it's very nice to start small and we get bigger, 1, 20, and maybe like at the end 1 million. So I've considered a very basic function, okay, so square with Gaussian noise equals 1. And in all of my plots, I will always have like in the x-axis number of iterations. So this is number of observations in the logarithmic scale. And in the y-axis, I will always have the distance to optimum in logarithmic scale as well. Okay, so here in that plot, I have in blue, I have in plain, I have before averaging, and in dotted, I have after averaging. So here, I consider on the left a decaying step size as 1 over root n, and on the right, a decaying step size as 1 over n. So the problem here is strongly convex. Okay, this is like a strongly convex function. So here, what should I get? First, if I look at, so here I'm considering several values of the constant. And so first, if you look at that plot, so if I have a step size which is bigger than 1 over root n, before averaging, I'm converging slowly. Okay, and this is just highlighting that fact, is that the convergence is proportional to the step size. So if your step size decays slowly, you converge slowly. Okay, and if you look carefully, this is the slope of -1. So in the log minus 1/2. In the log plot, 1 over n to the alpha is a line of slope minus alpha. And as you can see, if I augment the constant in front of the step size, I go slower. And if you look very carefully, this is a geometric sequence, 1, 5, 1/5, 1, 5, and this is like a linear spacing in the plot. Okay, so just highlighting the fact that the final performance is proportional to the step size. But when I do averaging, they all end up being on that line, which is of slope minus 1, and it does not depend on the value of C. It may take some time before I reach that value, that regime, but once I reach that regime, nothing is changing. It's just an illustration of typically two behaviors of an algorithm. You forget initial conditions, and then you reach the final regime where the noise dominates. Okay, so this is how it works. The key is that the choice of C. Okay, so if you look at the choice of C, so if C is too large, okay, then this is a blue curve. You start by diverging. Okay, it's not very good. And if C is too small, then you see that you're going to slowly converge like that. Okay, so here I want to highlight this because between this value which is too large and this value which is a bit too slow, there is one which is a black hole which is good, but the factor is 25. Okay, so this shows that for a problem dimension 1, strongly convex, a factor of 25 in your step size may be a problem. Okay, so just to have the fact that setting up C is not very easy. Now, if you go from alpha to 1/2 to alpha equals 1, then things are a bit different. Okay, so if you go back to my bound here, before averaging, there is this term. So I said that I forget initial conditions exponentially fast, except when n gamma n tends to a constant. So now I lose this exponential convergence, and what you obtain is that if the constant is too small, you go really slow. Okay, you can show that if you take a constant of C over n where C is too small, you get arbitrarily slowly at a rate which is still converging. It goes down to 0, but very slowly. And now if you take C being too large, you diverge again. And if C is 1, you get this nice 1 over n to minus 1. So here, why is this one better than this one? Because for all values of C, I end up converging at a good rate. Okay? Whereas here, I need to get C in a very subtle way so that I do converge at the correct speed. Okay? This is why people tend to do this. Yeah?
When you say averaging, you mean that you average the previous iterate and in the next estimate you evaluate the gradient in the average?
No. Okay, so it's a good question. So when I do averaging, it's always like I think it's I have it. Yeah. Ah, no, I don't have it here. I have it there. Okay, so if I go back there, it's not there. Yep. Thank you. Okay, so here, as I said earlier, there is no interaction between the algorithm and the averaging. You just, at the end, output the average iterate instead of outputting the full iterate. Okay? So there is no interaction.
And it's not interesting to put it in the evaluation algorithm.
That's a good point. No, it's not interesting, and if I remember correctly, it doesn't change anything. In fact, it may slow down the algorithm. It may slow down the algorithm. Okay? And in fact, one problem with averaging, you see here. Okay? So let's take the curve, here the curve in red. Okay? This is before averaging, you're almost there. So since averaging the entire task, this will slow you down. So typically, averaging slows you down. Okay? So it is customary to start averaging after a while. But after a while means add a new parameter. Okay? So this is one effect of averaging. It's hard to see when to start. And in the bound, you see it with this forgetting as 1 over n squared and not as exponential anymore. Okay? So you lose a bit by averaging. You forget initial conditions a bit slower. So this was for strongly convex. Okay. Now let's look briefly at non-strongly convex. Forget about that line. So what do I cover? I cover the fact that in the smooth situation, if you do averaging, you get this rate of 1 over root 10 with averaging. So the key here, when you look at those two setups, simple like while condition, ill condition, there is a single step size which appears to be reasonably good. This is the decay as 1 over root n. Why is it good? Because for the simple problems, it will achieve 1 over n, and for the hard problem, it will achieve 1 over root n. Okay, all other step sizes will be worse, at least for the math. So if you look, very simple, still in 1D, okay, I will have examples in bigger D in a moment. Okay, so on the left, the power 2, so you see the smooth function, which is strongly convex around the optimum. On the right, the power 4. This one is not strongly convex. It's not strongly convex because the derivative is 0. The variation is 0 at 0. Okay, so just the most basic example of non-strongly convex function. Then I'm considering again like several values of the decay. Okay, this is the decay. This is 1 over 1 half, 1 over root n, 1 over n, 1 over n to the 2/3, etc. Before averaging in plane, with averaging in dotted. If you look in the strongly convex case, we essentially recover the fact that before averaging, you don't do very well, and after averaging, you end up all following the same line. Okay, so just recovery of the strongly convex result. This one is different. You can see that, okay, so the before averaging, you have this ordering, and after averaging, you have the inverse ordering. Okay, so this is quite common in those problems. Is that before averaging, you're going very slow, okay, but as soon as you do averaging, you get very fast. And this is, and if you take this 1 over n step size, averaging does not help much. And this is what I mean by robustness to ill conditioning. The 1 over n step size can be arbitrarily slow if you have like a problem where around the optimum you are not strongly convex. Okay, so this is like in 1D, but there are many more examples by Leobodu's webpage in more than 1D. Okay, so the key is when you go smooth, you can start to look at the rate at which you forget initial conditions. Okay. So let's look at that. So what I've shown, what I've shown there, okay, this is the fact that the step size 1/2 was adaptive to conditioning, but it turns out that the bounds are a bit complicated, and if you want to go logistic, things are much sharper. So let's go logistic for the moment. So if you go to logistic, okay, this is your logistic regression. Okay, so this is you have data xn, 1n, you have d features. You have d features, and fn is of that form. Again, I'm limiting the test error. The problem with logistic loss is that this will never be strongly convex. So why this will never be strongly convex? Because the logistic loss as a log of 1 plus the exponential is something like that. So this is convex, this is strongly convex over there, but at the end you get a flat part. So this means that if you don't constrain your predictors, then it will never be strongly convex. So it's never true that the function is globally strongly convex. What you have is that locally, around the optimum, it may be strongly convex, but just locally. So what is typically done is, okay, if you're not strongly convex, you just make sure that you bound your predictions like this, and then you become strongly convex. The issue is what? Is that the value of the second derivative there goes down to 0 exponentially. Okay, so you end up with bounds which are exponential in m, which is not valid. So what you could do for logistic, in fact, you can show adaptivity to local strong convexity. In the sense that you take mu not being the lowest eigenvalues of all possible Hessians, you take mu as being the lowest eigenvalue of the Hessian at the optimum, okay, which is of course much bigger than the overall minimum of all Hessians. So this is what the new mu, and what I was able to show is that with the step size as 1/n, then you do get adaptivity to strong convexity, which is not local, in the sense that you get always 1/n, this is what you would get anyway, but now you get 1/nu, and nu is the local strong convexity constant. So this type of result is shows that logistic integration with HGD, which is what makes the money. Okay, so many of those search engines, they use like versions of logistic. This is like a money-making algorithm, is working better than expected. Okay, why? Because it does adapt to like local curvature. Okay, this may look like very like picky, but this is why it works. If you're not adaptive to strong convexity, this means that around the optimum you may need like to change the step size. So here it shows that a big step size is enough to get the optimal result in a purely adaptive way. No need to tell in advance what is new. You just need the radius of the data, and that's enough to obtain the optimal match. Okay, so this is a type of analysis which does not create any new algorithm. It's just saying that the reasons why it works so well are a bit different, but this is one of it. So the proof, I'm not going over the proof. I will just like mention a few things about self-accordance because this may be useful to someone. What? Yep.
How do we even care about the radius of the data? Can I just centralize my data and both produce 1 and error is 1? Why do we care about big power? If I centralize everything, R is 1.
For two things. First, okay, so if you went to the French training of physics, you should always have a unit somewhere. Okay, so R is a unit. Okay, so if the phis are meters, my thetas are inverse of meters, and my R are meters. Okay, and this is when you say R because it's a radius. Okay, and it's always nice to have this because you show that you make no mistakes. When I teach a class, okay, I know in advance that the step size has to be 1/r squared. Why? Because the step size has to be homogeneous to 1/the square of my data. Okay, so by homogeneity, you avoid many mistakes. Okay, so this is the main reason why I like to keep R. I could have said from the start, I will always see that the radius is bounded by 1. Okay, and then when you want to apply it, where do I put back R? Okay, it takes a while, and I'm willing to bet that among like 100 people, 10% will make a mistake in putting the R back into the algorithm. Okay, so this is why I always keep. I try to avoid doing like non-homogeneous things. For example, like R. So here you know that R times theta, this is good. This is unitless. So I'm allowed to put R times theta close to 15. Okay, so this is one of the reasons. And so in practice, so you need to know R. Okay, so one possibility is to threshold R, either divide all the data by the maximal norm to get one, or sometimes to clip the outliers. Okay, but the homogeneity, I really do insist on it because it gives you like immediately if you have a mistake or not. Okay, so the proof. Okay, I won't go over the proof. I will just highlight these properties of self-concordance, which is very useful in optimization. So what is this? This is that for a convex function in R, this is the fact that my third order derivative is bounded by a power of my second order derivatives. So here, Y is preserved for homogeneity. Okay? Why? Because if I assume that I multiply my t by 2, okay, so you should think about like f third to be like d phi over dt cube, okay? 5 seconds to be d phi over dt square. So if you want the units to match, it has to be 3 thirds. Okay, so this is the reasoning behind this affine invariant problem. And this property is satisfied for square functions, logarithms, and a bunch of others. And if you want to show the proof of quadratic convergence of Newton, it's very simple if you assume this. Okay, if you don't, it takes you a lot of pages, and you get very weird results. And if you want to know more, there's a nice chapter in the book by Boyd and Vandenberg, which applies, which is very interesting. The problem is that in our setup, few functions in machine learning are self-concordant. What you have instead is that logistic will satisfy this. The third order derivative is less than the second. There is no power of 3 thirds. This is the fact of life, and this can be shown by taking derivatives. So this means that if you want to use like such assumptions, you have to rederive a lot of steps, a lot of like data analysis, which we have done. And at the end, is the way to get like to do as if your function was a square function, but still have a result which is applicable to all functions. Okay, so this is really for the experts. But if you need like bound or logistic, this is typically the way. Okay, so this was the bound from before, but this one is a bit disappointing. Okay, so you get 1 over root 10, 1 over n, in the sense that we have a very specific problem. We have like logistic. Okay, so it's really smooth. Okay, so and I get this adaptivity. Okay, so compared to there, I do the best of this and that. Okay, the second algorithm. It's already not too bad. Okay, in the sense that if I use smoothness, I can get adaptivity. But could I also remove the mu? Okay, so if I remove the mu, I become robust to end conditioning, and this is the goal of now. So to do this, I'm going to assume I have least squares. Okay, so least squares, this is the least square loss. So in that context, stochastic value descent is often called like SGD. Okay, so this is like LMS to me. Least means square, LMS, and typically it is analyzed with the decaying step size. So what we propose with Eric Moulin, like 2013, is to take a constant step size. Okay, really a constant. Give me the ranges of your data. You take that constant, and so that constant being depending on the norm of your data. You need to assume that the noise is bounded. Okay, you don't need to access the noise level, but you need to know it for the bound. And what we proved is that the distance to optimal, so here f is the test error again, theta star is the optimal value of the test error, the minimizer of the test error, theta bar is my average iterate, and this is random. The expectation is over the randomness of the data, goes down to 0 as 1 over n times some constant. The noise, my predictions, okay, plus the distance to optimal, expressed in square distance. So for the experts in the room, there is a sigma square d over n, which is here, and this one is unimprovable in the sense that, for least squares, in the sense that give me n data points, even if you have infinite computation, you cannot beat sigma square d over n. Okay, it's a bound which has no model of computation, it's a bound which you cannot improve on, regardless of computation. Okay, so this one is unimprovable. And this one, as we will see, will be improved later. So this is achieving this 1 over n in a very simple way. Okay, so here is it the proof. I will not go over the proof. So I will go over more about the. I will go over why is it 1 over n. In fact, you can show this 1 over n convergence without any computation, just by looking at the setup of the problem. So you have here my this square, my Fn, the square. This is the gradient of the least square loss. This is the residual times my feature. This is nice. Like all stochastic gradient, the theta n form a Markov chain, okay, because the past is summarized into theta n and so on. But because my step size is constant here, I get this homogeneous Markov chain. The dynamics is always the same. And then, when this is the case, you can show that you of course need to add some assumptions that the Markov chain converges to a stationary distribution. Okay, stationary means that at the end, we end up like oscillating around the true value with a given distribution. Okay, I will call pi of gamma that distribution, and theta bar of gamma this average. So we know from the start that when you have a constant step size, it is not a converging algorithm. It will oscillate forever. Okay, so this is known for Markov chain theory. But the key is that for least squares, since you can invert like gradient and expectation, you can show that it does oscillate around the true value. Okay, so and this means that if you do averaging, okay, then you get to converge to the expectation under the stationary distribution. Even better, you have like several versions of so-called like ergodic theorems that will tell you that you do converge at rate 1 over root n. Okay, the distance to optimum will be 1 over root n. So since we measure performance in square norms, you get this 1 over n convergence rate just by the Markov chain setup of the problem. So because we have a constant step size, we do have a Markov chain, so we do have the ergodic theorem which applies, and hence convergence is 1 over n. Of course, you still have to find what is in front of 1 over n. So this requires quite a bit of work. But the key is that because we have this constant step size, we forget this very quickly. Okay, very quickly with the constant step size, you get around there, and averaging will get you. So this is the algorithm. Let's look at a bigger data. Okay, d equals 20. So just to highlight the convergence. So again, in the x-axis, this is this number of iterations in logarithmic scale. In the y-axis, this is distance to optimum in logarithmic scale as well. In dotted, this is like before averaging. In plane, this is after averaging. I'm considering like 4 different step sizes. Constant step size with several values of the constant, and turquoise, which is a decaying step size. With the decaying step size, you recover what we saw before. Before averaging, you get this 1 over root n convergence, okay? And after averaging, you get back to that line, but a bit later. With the constant step size, before averaging, you don't converge, you do oscillate, okay? You get closer if you get a smaller step size. This is predicted by theory. But as soon as you do averaging, then you go to this like unique line, which is the sigma squared d over n. So this is an illustration of the fact that before averaging you don't converge, and after you do converge. Okay, so this is the illustration in very small data. And now let's look at bigger data sets, which are like standard benchmarks in machine learning. So on the top you have the alpha data set with 500 features and 500,000 observations. And on the bottom, news, which is like the typical of a news data, web data, which is a lot of features but very sparse. Okay, and I'm sure that Nicolas Leroux tomorrow will like add zeros on top of that for that problem. I don't know how many zeros, but a few. And okay, so bottom alpha, top alpha, bottom news. So why 2 columns? Okay, so why 2 columns? Because optimizers are nasty. Okay, I'm one of them. Okay, so I'm allowed to criticize myself. And typically, what they say, okay, is, oh, look at my bounds. They are nice. With that step size, I get that bound. It's optimal. It's great. okay? And then they go over simulations and they change the step size, okay? Because they feel that the bound is nice, but the step size does not work well in practice. So why 2 columns? On the left, the step size from the bounds. On the right, the step size optimized after a few iterations. Okay, so here, let me parse these slides. Again, number of iterations in log scale, number of observations, number of iterations in log scale, and distance to optimum in log scale. So here I'm using real data, which is finite. Okay, so I don't have access to an infinite stream of data, so I have to split it into train and test. So I learn on the train by sampling the replacement from that data, okay, and I test on the test. So the error that I make at the end is cannot go to 0. Okay, at one point, it's the best I can do given my training data. This is why all the curves level off. Okay, they level off at the optimal test error that I can achieve given my training data. Okay, so this is why they don't go over there, because I have access only to a finite amount of data. So here the black line dotted, this is a single pass over the data. Okay, so this is what the performance after I see the data only once, and then whenever I go on the right, I'm doing several passes. This is the logarithmic scale. Okay, so when I go from there to there, essentially I've made almost 200 passes over the data. As you can see, so several things to be seen, that after a pass over the data, you're not doing, for the constant step size, you're almost there, but doing a few more passes will help. This is related to one of your questions, is that doing more than one does help. If I were to do many more, I will diverge, okay? Because then I will start to optimize the training error. In fact, there is one of that later, I think, for logistics. But for this one, there is no divergence after 200 passes. Fine. So doing more than one pass in practice does work better. So now let's compare left and right. So on the left, I'll take the step size from the bound. Typically 1 over r square root 10 and 1 over r square. Forget about sag. As you can see, the behavior of the constant step size is pretty good. Then it converges quickly, whereas the decaying step size goes very slow. Okay, so this is essentially after 10,000 iterations, I have not moved at all. Okay, so it is very slow. Now, if I start to optimize the step size, and the step size is optimized what? Is optimized so that I run many values of C's and I compute the error at that point after a single pass. So I'm being very conservative, I'm being very helpful to the algorithms by running them for a single pass, testing all values of C and taking the best one and reporting just the best one. As you can see, for the constant step size, there's not so much of a difference. Okay, optimizing the step size does not make a big difference. So here I took a grid, okay, in C's, and the grid was not fine enough to see a difference. Whereas for the decaying step size, if you want to be good at that black curve, at that black moment, you want to be good there, you have to take C so big that you start by diverging. Okay, so that value of C here, okay, to be correct after 500,000 iterations, causes you to diverge at the start. This is log scale. Okay, so log scale means that the error is multiplied by 10 when you start the algorithm with such a big step size. So this highlights the fact that a good step size should not decay as fast as 1 over root n, and the constant step size does well in that setup. Okay, so this is a very simple simulation to highlight this, is that if you want to be correct at the end, you have to take C so big that you start by diverging. A constant step size does not have that. So this is a good thing about the constant step size. The bad thing is, if I take C too big, if I take C beyond 4 or even 10, this will diverge. Okay, so the step size is big, so it converges quickly, but you cannot play around it too much. So this is for the alpha data set, and for the new data, this is quite similar. In that, if you don't optimize the step size, you're very slow for the decaying step size, and faster with the decaying step size. Faster if you start to optimize the step size, whereas a constant one will get you there. Okay, so this is the yep.
The right plot is good for analysis, but for real data, with no theta stars, we cannot compute the error, so we cannot
So I think that you are. Okay, so typically, okay, so in practice, what I depend what you do. If you want to resolve many times the same problem or not. Let's say I'm doing computer vision and I'm training neural networks like deep learning. Okay, I've been doing. Let's say I've been doing this like for 2 years. So it's always the same problem. So I can use my knowledge of the previous problem to get the good decay of the step size. Okay, but if you solve like a new problem, it's easier to get like a universal step size which you launch. It may not be optimal. You may like do a bit better if you optimize. You're sure to get the correct solution. It really depends whether you solve a problem once or several times. Yeah. So I have 20 minutes left. Okay. So now we'll go quick on this one. Just a word of caution. Okay, I've said that at one point, sigma squared d over n was optimal. You can't beat it. And now I present simulation where d is 1 million and n is 20k. And d over n, that setup is not very small. Okay, it's very big. So what's happening? It's happening that this optimality is true over a class of problem which is too big. Okay, so my problem is a bit simpler, and what I will not have time to talk about is the fact that if you look at the data that I have, here I'm plotting the eigenvalues of my covariance matrix. Okay, so they go down. This is log number of eigenvalue, log of the eigenvalue. They decay quite rapidly. Okay, so this means that it may be possible to leverage the fact that eigenvalues are decaying to improve on sigma squared d over n. And what I have done with my student Emeric Diolveux is exactly this, showing that SGD is adaptive to that kind of behavior and can improve on sigma squared d over n given some nice decaying eigenvalues. Okay, so there is details which I won't go over. One thing which is, let's forget about that, okay. One thing, yes, one thing before I move on to the last part is average radial descent. We have seen that it was achieving this balance term, it was optimal, and the decay as 1 over n. Okay, so this is what we have. What I showed earlier on today was, if I apply just acceleration, let's start acceleration. Okay, let's forget about like problems with noisy gradients. What you can show that you will get like a 1 over n square for the forgetting of initial conditions. This you will win, but acceleration is known to be non-robust to noise. It's like conjugate gradient, and you won't converge. The variance term, the noise of the problem will make you not converge. This does not go to 0. Okay, so this is the current state of the art. If you want to be optimal for the variance term, you have to do average radial descent. If you want to be optimal for the rate at which you forget initial conditions, you have to use acceleration. So what we tried first with my student Nicolas Flammarion was to go in between, having a mix of the two, and we end up with a mix of the two. Okay, so we get, when alpha is 1, you get that acceleration, and alpha is 0, you get back average radial descent. And in between, you can have a trade-off between those two. And if you take alpha being whatever, you get a trade-off. Okay. What we did more recently with my two students, Emeric Diolveux and Nicolas Flammarion, is achieving the two optimal results. Okay, so forgetting initial conditions at the proper rate and getting this at the proper rate as well. This is like very recent work. And if you want to know more, we can discuss. Only for least squares. Okay, so now, before I move on, there is this issue of, okay, the money comes from logistic. You may think, okay, it's nice, these squares, there's a nice way for these squares, but what happens with logistic? With logistic, this intuition about Markov chains can still be applied. So I have my Markov chain. It still converges to a stationary distribution, and which is such that the average gradient is 0. But now I don't have a linear gradient. So I cannot invert like gradient and expectations. So this means that the gradient at my expectation is not 0. This means that if theta star is my global, my best predictor, I'm oscillating around the incorrect one. This means that if I do averaging, I go quickly to the incorrect one. Okay? So this was known from before. It is known as constant step size stochastic gradient is not convergent beyond the squares. And if you take this that type of data, before averaging you do oscillate, but after you converge, you flatten out, but to the incorrect value. So what I will not have time to present is replacing this by something like that. Okay. So there is a way to restore convergence for this. There is a way to restore convergence for that problem at zero cost. At twice the cost of SGD. And the idea is to do a Newton step. Okay. And you do an online Newton step, which still has a complexity O of D. So you replace that line of code by that line of code. Okay. So trust me, I won't give you the details here, but you recover this convergence. And we can probably this robustness to the condition. So what I want to get at is finite data. Okay, so this is what I'll come back to that later. Yeah, so this one maybe has a good summary of what we have seen so far. So we have seen, okay, so we have just added that line. Okay, so we have seen that when you're smooth, we are not able to really improve on the rates of stochastic. We can use smoothness to be adaptive, we can use smoothness to characterize how fast we can forget initial conditions, but we couldn't use it much. If you go quadratic, we were able to essentially get to this d over n for one part and 1 over n for forgetting of initial conditions. So you can see that we are still very far away from deterministic. Okay, so deterministic, in the strongly convex case, is exponentially convergent. Okay, so we go from exponential to 1 over n. This is pretty slow. But here, remember that this is for training error, this is for test error. What I will present now is situations when you have a finite sum and we are able to recover this exponential convergence rate. But of course, we have a price to pay, and the price to pay is that we now optimize the training error and not the test error. So let's go over. Okay, so remember. So if you want to remember a single thing from today, is that when you use that stochastic gradient, you optimize the test error. Okay? So showing a bound on training error when you use HGD is kind of useless because you have a bound on the test error. The problem is that this only accounts for a single pass over the data. Okay? As soon as I see the data point twice, my bounds are not valid, and if you do too many passes, it will end up overfitting. The other approach, which is what is done in practice, you do multiple passes. As soon as you do multiple passes, you start to optimize the training cost, and you need to regularize to avoid like overfitting. What I will consider now is this setup where I have a finite set of functions like this, which is you have a finite set of functions, and you want to optimize. So we have seen already like two algorithms to do this. When I have a finite set of functions, this will be like typically a loss plus regularizer, but this can be applied to any finite sum. We have seen batch gradient descent, which is at time step t, I'm going on the negative gradient. So if you assume transconvexity, we have seen this is like linearly convergent, but the issue is that at every time step, I have to accept a full gradient. Okay? So this is essentially batch gradient descent. And the way it behaves, it goes make a few big steps. We have seen stochastic gradient descent, which replaces a full gradient by a single stochastic gradient. You select a function at random, okay, like this. You select a function at random, and you take a step in the negative gradient. So by design, the cost by iteration is independent of the number of functions. Okay, so this is by design O of 1, but we have seen that the convergence rate is 1 over t. Okay, so you get the image to have is make a lot of cheap iterations and you end up converging. So this is like the classical techniques, like in the single slide, batch gradient, a few big steps, SGD, a lot of small steps. Even like in a more like, this is like the trace wish list. Okay, so we plot what you want, you plot what we plot what we have, we plot what we want, and we hope to get it. Okay, so here I plot again time now in the no logarithmic scale, and the time distance to optimum in logarithmic scale. So deterministic is a line. Why a line? Because if you're strongly convex, you get exponential convergence, so the log is a line. Okay? So you have steps. Why do you have steps? You have steps because before you make a single step of Bach gradient, you have to look at your entire data. So you do nothing, look at the data, make a big step, and go on. So for a while, you don't do anything. Whereas stochastic gradient, as soon as you see a single function, you start to make progress. Okay, so you make strong early progress, and then the performance levels off. If those converge, it goes slowly. So the hope is to do something like that, which will start as fast as stochastic, and then go linearly again. This is the goal for the last 5 minutes. So this is the joint work with Nicolas Leroux, who's going to be there tomorrow, and Mark Schmidt. So the algorithm has also like 2 lines of code. So the idea is to keep in memory the gradients. Okay, so this means that whenever we select the function, we're going to select the function at random, compute the gradient, we're going to store it. Okay, so at every time in the algorithm, we have some old values and some new values. Okay, so the algorithm works as follows: I select I of t at random, compute the gradient at my current iterate. Then I replace my storage. So yit is the gradient of function I at time t. Okay, so if I select that function t, I update my storage. Otherwise, I keep my old values. Okay, so at every time step, I have some very recent values and some very old values of my gradient, but I have a value for everybody. I take this average of the value and I make a step. In a sense, this can be seen as a very lazy gradient evaluation. Okay, so I have to compute my full gradient. I just take all values except for one, which I take a new value. Okay, this is a super lazy gradient evaluation. First aspect, this is not a new algorithm. Okay, so this is like something which is, I think, interesting, is the fact that we took this from Blatt et al., which were doing a cycle to the data. Okay, when you have data, finite, and you want to do several passes, you have 2 choices. You go through the data and start again. This is cycling. Or you can select randomly from the data at every time step. This is something with replacements. And what we showed is that when you go from cycling to random selection, the behavior does change. In a sense, when you go like cycling, you can have a much bigger step size, and it can get you to a much stronger convergence. Of course, this has a cost, the cost of storage of the gradient. So this can be, when you do learning, and the gradients are proportional to your features, this does not need to be, you don't need to store all the gradients, you just store the constants. So it's over n. In terms of convergence, I will go quickly, but you get this exponential convergence rate. I won't give details, but this is what we obtain. And the proof don't care. This you don't care. This you don't care. This is just like a simple instance. So where we compare like several algorithms on the data set, which is quite bigger. So we compare like SAG, which is our new algorithm. So it does work as advertised. You start fast. So those are the stochastic gradient. Okay? You start as fast as stochastic gradient, and then you reach this like a linear convergence rate, and you optimize up to machine precision. And here, this is training error. Okay, so very important. This is training error. So you optimize the training error up to machine precision. This is rather useless in practice, but at least you can get a nice plot like that. Then this is like gradient descent. This is Nesterov in brown. This one is like with cycling. Okay, this is like cycling. So without like if you just do cycling, then you don't go very fast. And this is LDFGS, which is that. Okay, so here this is an example where we're able to get very fast convergence to precision very quickly. Okay, so here this is the number of passes to the data. So after like 30 passes, we were able to get like machine precision type of performance. So what do I say is this may look like going there is not important. Okay, going there may be. Okay, in the sense that the good thing about those techniques that you optimize, and if you do like 20 passes, you're sure it's going to work reasonably well, and you know that you should stop optimization. Otherwise, those ones you never know where to stop. So for test error, okay, so now I'm plotting like training error on one side and test error on the right. You see that at the end, after a few passes, they all get to a good testing error, but SAG gets it a bit earlier. Okay, so this is one thing that we have. So be careful that whenever you apply optimization to machine learning, you have test error, train error. Okay, so for stochastic gradient, we know that we implicitly optimize testing error, but for those techniques, you optimize train error, so you have to be careful with the testing pattern. Okay, so there is like other ways of doing this, and a very nice paper by Johnson and Zhang, like called stochastic balance reduction. A nice one by Aaron DeFazio, and maybe I should mention also like random coordinate descent, it achieves like similar one. But if you want to know more, you can look. All right, so let me just conclude. So maybe with a few master slides from those two lectures. The first one was the state of the art if you consider optimization like separate from statistics. Okay, you get like this 1 over root n convergence rate, but at the price of O over n squared d steps. Whereas if you do things directly, so if you use the stochastic gradient, you get the exact same test performance with a much faster algorithm, which you do like n step of SGD, which is O of the n, and you get the same behavior. Then we saw that those bands are a little bit too naive, as they don't take into account the rate at which you forget initial conditions. Okay, and this can be characterized if you assume smoothness. Then you have things for least squares and also for logistic. If you're willing to use online Newton, you can get robustness to the conditioning. And finally, stochastic adaptation. Okay, so this is like the final table. So my hope is that you can see on all of that, I've covered all of that. Okay, so if you take any place, there is somewhere on the slide where I'm doing this. So the key is that big take-home message: strongly convex is easier than convex. Okay, it's an easier problem, but problems tend not to be strongly convex. The modern ones. Problems from the 50s, if you optimize the function in 2D, yes, it's going to be strongly convex. If you optimize in like high dimensions, you're more in that. And then, as you put more assumptions to the problem, things get easier. Okay, so if you optimize the quadratic, it should be easier than the range loss, and this is it. So, in terms of, I was asked to give a few open problems. So there's a lot of problems that people are currently working on. And so the first one is what I call non-parametric stochastic approximation. So this is like doing like essentially kernels. Okay, so if you want to run like all of that for a kernel machine, then the problem is that you have to compute the kernel metrics. This is over n squared from the start. Okay, so the idea would be, is it possible to reduce the cost from O over n squared not to O over n? Okay, it will never be O over n. Because if you're O over n, this means that you're parametric. You may not adapt to like data which is nonlinear. The hope is to get O over n times a small constant. This is still like, and I do believe this is why. Okay, so if you want my own take on why deep learning is ahead, why? Because it's efficient. Okay, so on many of those problems, you could not even run your SVM or your kernel method because it's too slow. Okay, so in fact, one of the reasons why it's working so well compared to the rest is because the optimization is still a problem. Standard prediction, I think, is a nice problem. In this class, I focus mostly on the square laws logistic because it's simpler, but a lot of problems arise when you go like to more complex problems. Going beyond a single path is really something which is a big open problem, in the sense that there is a mismatch between theory and practice. In theory, we say, do a single path. In practice, it always works better to do like more than one, 2, 3, 4, 5. Then finally, there is non-convexity, which I didn't like put, but I think I wanted to talk about. So all the things I've discussed today, okay, the proofs only apply to convex problems. Okay, the question is, let's say you're interested in the non-convex problems. Okay, sometimes some people are. The question is, what does go through? Okay, this is a debate whether what should go through. So the current answer, the classical answer to say locally it goes through. Because locally you are around a global optimum. Okay, so locally a function is convex. This is like only partly true. In particular, there is evidence that one of the key problems with non-convex optimization is not local minima, it's stationary points. If you take gradient descent, okay, it typically gets stuck in a stationary point. Okay, so folklore says that if you move the system hard enough, you're going to escape all stationary points. This may not be true in high dimensions. Why? Because if you have a single direction to escape the stationary point, finding it by mistake is unlikely, by chance is unlikely. To me, non-convexity, the first challenge is being robust to a stationary point. And finally, big open problem is going parallel. Okay, so I think that we have reached on the single processor. I think we have reached like a level of sophistication which is, to me, like for me largely enough. That we start to have matching upper and lower bounds. When you go parallel, okay, things do break down. Okay, if you take any of those algorithms which are presented, there are many ways of making them parallel, and I'm sure Nicolas Leroux will mention them. Things get difficult. So ideally, you want to preserve the speedups. Okay, so let's say, take that slide. Ideally, you want this to be preserved in the distributed setting. Okay. The problem is that those new techniques, okay, for example, this one which I know quite well, is not really robust to having delayed gradients. Okay, so if you have a gradient, when you have an error, this will not be very nice. Whereas if you take like the slow techniques, they are quite robust. Okay, so you slow, but you can apply to a higher number of processors. One key issue when you go like to multiple processors is when I go from 1 to 2, you don't want to lose anything. Okay, so if going from 1 to 2 means I need not to use this, but I need to use that, then when I go from 1 to 2, I lose a lot. Okay, and before I recover from going from a single machine to multiple machines, I need a lot of machines. Okay, and I believe that many problems which are solved like using a cluster could be done on a single machine done correctly. But for people like Nicolas Leroux, you have no choice. And this is still like a good source of open problems, really how to make things like parallel, because really you have a lot of applications, and I still believe that there is like new algorithms to be discovered. And on this positive note, I will end and thank you for your attention.
Maybe we have time for questions.
Yes, so it may be more crucial for the non-convex optimization, but what about adaptive learning rate scheduling algorithms?
Oh, okay. On some versions of my site, I do have this as an open problem. Line search for stochastic is also a big open problem in the sense that right now this is really trial and error. So you augment the step size, you see the validation error goes down, and if not, you move. So this is something which is still an open problem. How to adaptively set the step size. So on the single machine, if you assume convexity, I think those algorithms that constant step size does sort of solve the problem. You take a very big step size, and then you're fine. If you're non-convex, and that will not work, that setup, then this is still an open problem. But clearly, this is something which is it's very hard because the problem, so when you do line search in the deterministic setup, you have access to the error, compute the function value. In the stochastic setup, you need to waste samples to compute the test error. And should you use your samples to do a step or compute the test error? It's always an issue. So if you do both, at one point you will overfit.